Hi, everyone. Thanks for coming. What are we doing today? So, oh yeah, I need one other thing. First off, logistical things. Today is the last real lecture where I talk at you for an extended period of time. Next time, you will talk at me for short amounts of time. And that should be fun. Change it up a little bit. I'm excited about that. So everyone knows, yeah, lightning talks next time. I'm going to post an announcement and like force you guys to like upload your slides so we can get them all on one laptop, so we can kind of just bang things out. Homework due tonight officially. I'm good with that. Yes, excellent. Anybody have any thoughts, questions, comments, issues? Everybody good? Excellent. Okay then. So let's get into it. So last time we did how to drive a car. Very fun. Today is a somewhat dramatic change of focus, I suppose. Today, I'm going to give you like my very biased, idiosyncratic, highly opinionated tour of reinforcement learning, which we haven't talked about very much in this class. I have lots of opinions on this. Take everything I say with lots of grains of salt, I guess. And like, you may have other opinions, you may disagree with me. Feel free to argue. I'm all about it. Speak up. That'll make things more interesting for everyone. But yeah, so today I want to kind of like, we'll do like kind of a brief tour of reinforcement learning, and then dig in a little bit into like policy gradient methods, which probably everyone's heard of. Who's done policy gradient before? Yeah, so most of you guys have seen a lot of this stuff. And then kind of finish up with like, I don't know, a little bit of commentary on like challenges for the future of kind of, you know, our field and stuff like that. And kind of where the fun stuff is in terms of research problems and things like that with all this stuff. Okay, cool. So let's start out with, just to, you know, go way back to basics. We're going to start back up with the original optimal control problem that we've been looking at. So minimizing over states and controls. Basically, I'm going to derive like the policy gradient stuff with the same notation and setup we've been using in here, with X's and U's and minimizing costs instead of S's and A's and maximizing rewards. It's all the same stuff. So here's the problem we're used to. Cost function, stage cost, right? Additive cost, and then our dynamics constraint. And we know, you know, cost, dynamics, and maybe other stuff too, right? Okay, so the big question of the day is, we've kind of hinted at some of this before, but basically, what do we do if we have no dynamics model whatsoever? What if we don't know anything about the dynamics of the system, right? And I would argue in a not even very like tongue-in-cheek way that what you should do is probably get a dynamics model somehow. That's probably the right move. And in practical engineering context, I'm like, I can't think of too many situations where that isn't the right move. Can anyone actually, does anyone here have counterexamples where you wouldn't want to build a model? Or have any good ones? Yeah.
If it's just for like a very rough prototype where you don't need it to be precise. PID.
So yeah, you could do PID. I mean, you can always do PID. I would say in like, let's say a more complex control scenario where you like want to do, you have a big complicated thing and you need like PID won't cut it, let's say. Yeah.
You have a bunch of tasks and you want an experienced end users to be able to program those tasks.
Yeah, that's a good one. I have lots of thoughts on that, I guess. So there's been some really cool work, some of which I just saw it at my first conference last month that I went to, on like developing high-level GUIs to like, and Boston Dynamics has done a lot of cool work on this, where they've had like choreographers and like artists come and design, motions for their robots with like kind of animation tools and high-level GUIs that are sort of suitable for users. So I think like, and they're doing all optimization-based stuff, right? So I think there are ways of like setting up, like keyframe poses, this kind of stuff that are okay. But yeah, I don't know, do you have something more specific? Like, what did you have in mind?
I often think about like kitchen tasks, but for that, like, yeah, you might know your robust dynamics, but you might not know the dynamics of everything in the environment, where it makes it very hard to model. Ask the end user to do that. They have the capacity to model everything they might see in the kitchen.
So you mean though, like you would like to do like kind of imitation stuff?
Yeah, if I want to have my robot cut a bell pepper, right?
Yeah.
I've used a bell pepper before. Unless I am a roboticist, I would not know how to inform the robot what it needs to, or I may not know how to inform the robot what it needs to be able to cut that bell pepper.
Yeah. So what would you do? What would you do that would be model free there?
I think model free, you can go the imitation learning route. You can have a selection from some set of policies that you believe will be able to decompose to the task.
Yeah.
Obviously, I'm super biased, whatever I'm working on. So these are the things that I.
Yeah, no, I think it's super interesting. So when I say model here, to be clear, I don't necessarily mean like an analytic physics-based model. Like learn models, are totally cool. Like, yeah, et cetera. But like the idea of having a model versus not having a model at all and just trying to directly optimize a policy or whatever is more like, yeah, anyone else have any thoughts? Yeah.
But if you have like a bunch of states, if you have like something connecting with octagons, you have like a snake thing or whatever, states that it's really hard to model that.
Yeah, I mean, so in that situation, like, I would say like if it's actually, that's not that bad. Like it might be high dimensional, but in principle, that's like analytically modelable. And if you didn't want to do it analytically, like you could go do a bunch of experiments, collect a bunch of data, and then like solve a regression problem or supervised learning problem, right? To fit a model to the data, right? So yeah, like, does anyone else have any thoughts? Yeah.
I mean, this might be, I'm more interested to see what you think about this.
Yeah.
Like, what about like recovery policies for like a rugged robot? Like say like, like it's sitting on ice and like you want like one policy that like recovers from like those specific examples that like you may have learned.
Yeah, no, I think these are really good. So in that situation, you want to recover from like arbitrary crazy things though, right?
Yeah, I guess like.
So my point there is that like, if you don't have a model for that, that means you have to have experiences for all of these things. Whereas if you have a model that like, sort of can describe a bunch of those things, then you can potentially generalize much better to like things you haven't seen yet.
Just to clarify, where are you drawing the line at having a model versus not having a model? Does it extend? I'm assuming it extends to model-based.
Oh, absolutely. Yeah. So
it extends to stuff like active or methods where you're kind of learning a model with rewards.
So I wouldn't, so what I mean specifically is you have a model, a dynamics model, a dynamics function somewhere in your algorithm, as opposed to not. So I would not include like actor critic where you're fitting a Q function or value function approximation in this. I would call that model free still. Yeah. So I mean specifically dynamics model.
Okay.
Anybody else have any thoughts on this? Okay, let's keep moving then. Okay, so yeah, basically the RL thing, I would say, is essentially just is optimal control with no like a priori model. So we're solving the exact same problem. We have a cost function. We're just assuming that we don't have this anymore. It's not given to us ahead of time, right? That's basically it. It's the same problem otherwise. And like the dream of RL is to develop algorithms that can figure out how to achieve control tasks by somehow performing like trial and error experiments on the system, right? To figure out what to do. That's sort of the dream, right? And like I would say, really the dream would be to do this on hardware, right? Do it on the robot. We kind of, can't necessarily do now, but that's the dream. Okay. So lots of ways to do this. It's obviously a super hot area for the last like decade plus. So, and you guys have probably done more of this than I have in some cases. So options. The first one maybe to talk about is model-based RL. And I would argue this is actually, people have been doing this forever, as long as we've been doing control. And roughly speaking here, like what you want to do is learn a model. Say we'll call it F sub theta of XU. Then use or simultaneously use sort of the standard control techniques we've talked about or others, kind of whatever, to then do control. And to kind of make this a little bit more concrete, what you're doing here is you're taking a bunch of data and fitting your f of XU. So you might have a bunch of, you do a bunch of stuff on the system, you drive it a whole bunch of ways, you collect a bunch of states and control. So the X's and U's here are all things you did on the robot. And then you solve this sort of, regression problem over the function f. So this is some kind of parametric function. Let's see. So these are all data you collect. And then this guy is some function approximator, parametric function, model, whatever. With parameters theta. So this could be anything from like a parametric model, right, where you wrote down some physics and it has unknown stuff in it, or it could be a black box like neural network and these are the weights, kind of whatever. There's a broad range, and there's a ton of examples of things like this that go back to well before anyone like called this stuff RL. Historically, I would say the roots of this lie in like adaptive control, which has been around since like at least the 50s, where people did various flavors of online gradient sort of descent on control parameters and model parameters, and long history there. And deep connections to like adaptive control in general. Okay, so that's like one way to go, which is seemingly not very popular at the moment, but I would say like has maybe some pros depending on what you want to do. Another thing you can do is Q learning, which is you learn an action value function. Which we talked about when we did dynamic programming, right? So this would be sort of a Q theta of XU. From a bunch of data, right? You do a bunch of stuff, put a bunch of controls, inputs in, collect a bunch of states, evaluate the costs of those states, and then you can calculate this thing if you do enough stuff. And then you can get your controls from this by solving like the one-step minimization that looks like, U equals argmin over U of Q X U. So yeah, this comes from dynamic programming that we talked about. So we have
Hey,
this
Zach,
guy. Yeah.
Why isn't it argmax?
Because we're doing the problem I wrote up there where we're minimizing a cost function.
Oh, I see.
But we're doing control.
Would like how would you interpret the value in the action value function?
What do you mean by that?
I guess I thought in like traditional RL, like value means reward or like the benefit of.
No, it means cost to go.
I see. Okay.
Literally cost to. I'm going to write exactly what it is right now. So it's this thing from the dynamic programming recursion. So this is when we do dynamic programming, right? We have the one-step cost, and then we have the cost to go from there to the goal. And inside there, we put the dynamics, right? So this is like classic what we did in class, right? For dynamic programming, when we derived LQR and a bunch of other stuff, and we talked about how, in general, there's this cursive dimensionality thing. This is terrible. The thing I want to point out, so basically what we're doing here is approximating this thing, right? We're doing approximate dynamic programming with some neural network in the mix to approximate the in this case, action value function, not cost to go or value function. Can anyone tell me why we're doing that? Why not learn V?
Because that requires having the dynamic.
Exactly. Yeah. So that's the whole game here. So we're going to take the whole thing here that's inside the min, and this is Q. And the reason we do this is so now we can be model free. If we learn Q instead of V, we never need the dynamics to do anything. I think we called this G when I did it because we used Q in the same set of nodes for LQR. But the standard notation for it is Q. So today it'll be Q. So yeah, I'm deliberately sticking with all of the conventions and notation we've been using in the class, which are not the same as like what is common in RL. So V is cost to go, right, in our lingo from control. So I will mix and match. I'll try to be as consistent as possible. So yeah, you can fit Q by just running lots of experiments and evaluating costs on trajectories. Yeah.
So is Q like a function of K as well, or does it change with K?
It can.
Okay.
Yeah.
I guess I'm asking, like, is there like a similar recursion?
Yeah, it looks exactly like this. Yeah, you can define the same recursion on Q. You just like do some simple tweaks to that. So yeah, it's literally like actually when we derived DDP, I did it in terms of the Q function. I called it G though because of notational overloading problems there. But yeah. Let's see. Okay. So that's Q learning. And then kind of the number 3 would be policy gradient methods, which we're mostly going to talk about today. because these have been super hot for the last several years, and like a lot of the major results and successes, I think, in RL for robotics have been these guys. So here the idea is you just approximate the control policy. So U of X parameterized by some thetas with whatever you want. So a neural network, if you like. And then you directly minimize the cost function with respect to the thetas to find an optimal or approximation to the optimal policy. So this looks roughly like min over theta of the thing we wrote down before, like our standard control cost. But we're going to plug this u in everywhere where this function u in everywhere, right? So now we get something like this. So we kind of eliminate u from the problem, and now we just have x's and thetas, right? So really, this whole thing now is only a function of x naught and theta now, right? And then essentially, so we do this. So given an x naught, it's basically just a minimization over theta. And the kind of standard move then is to use random sampling and a bunch of experiments on the system to estimate or approximate the gradient of the cost with respect to theta. And then you use that to do gradient descent. Rollouts on the system, collecting a bunch of trajectory data, and then it's just evaluating the cost. And if you do a bunch of samples, you get a bunch of those evaluations, and you use that to infer a gradient, and then do gradient descent, right? And then finally, kind of the last category-ish, are actor-critic methods, which basically glue together 2 and 3, roughly speaking. So you approximate both the policy. So you have like a u parameterized by theta of x and a q function, value function, something, something of that flavor. Q function, cost to go, whatever. And here you'd have different weights on this guy. And then you basically use them both together and jointly optimize. And essentially people do this because it helps with the convergence of the stochastic gradient descent methods that are used to optimize these things. Okay, and there are like infinite variations on all of these and various ways of smushing ideas from the different categories together. Let's see. And I would say like kind of the major like philosophical break from everything we've talked about before is that basically all of these algorithms try to assume as little knowledge as possible about these system, environment, dynamics, et cetera, right? You're kind of trying to avoid having to know anything about those things a priori. And I would say that philosophically, that's like at the core of RL versus optimal control. That's really, I would say, the main difference. Here's where I get sort of biased, shall we say. I would say like in a practical like engineering context and like a robotics context, say, I don't know that that's the assumption you want to make. Like you can generally do better if you know more out the gate. And usually we do know a lot about these things. Okay, so I will save some of that commentary for later. So let's do the policy grading thing. Like how many, I think a lot of you have seen this, right? Who hasn't done this before? Okay, a couple people. I think like the derivation of this is like kind of fun. There's like a couple of clever tricks in here that are cute, but I don't know. I have mixed feelings about the algorithms themselves. So these are super popular though. Like all of the cool stuff of the 2010s were variations on this, right? And it's still super popular. And also fairly simple to implement. Okay, so there's like a weird major assumption in here. I consider it kind of weird. So we're solving the optimal control problem we wrote up here that we've been solving the whole time. And we're assuming this is like a robot, you know, whatever. And it has deterministic dynamics, right? Like it is modelable, there's physics. It's not like crazy noisy or anything, right? But to make these methods work, you make a major assumption that the control policy is a stochastic function. Even if the real thing is not. And we write it now as a probability distribution. So it's a lot of times written like this, pi sub theta of u conditioned on x. And so it's like given some x, you have this conditional distribution that gives you like a probability over u's. So you'd say like probability of u conditioned on or given x. Okay, so because of this, even if we have deterministic normal dynamics, now the optimal control problem is now a stochastic optimal control problem, right? And the trajectories are stochastic, because if I run this controller, what I'm doing is drawing samples from the distribution as I run the controller, and it's noisy. So it's going to push noise through everything, right? So all the trajectories now, this induces a distribution of the trajectories, right? A state distribution, et cetera. So the whole thing's stochastic, even if the dynamics are deterministic. And we're going to assume they are. And I would argue, you know, most robotics problems are pretty much deterministic. So this is kind of a weird thing to do. So why do we do this?
So you can have expectations for like optimizing it. So like SGP.
Yeah, I don't know, like, why would you choose to do this? Yeah.
It goes to some exploration of the policy.
Yeah, you could argue this, but I would say like most of the methods that do this. So generally, these methods still only find local optima, right? They're not actually particularly good at doing exploration. So I'd maybe practically disagree with that. Yeah.
It might not be true for a lot of words, but for some words, they're modeling not exactly the robot I'm controlling. It might be a joint space with some other stuff in the environment, like the target or something that I'm manipulating. So I think in that part, if you do a joint space with this too, it might make sense to have this.
I don't think I followed that. Sorry.
Yeah, I mean, if there's a joint space between the robot you're actually controlling and some other, like say, moving target you're trying to.
Oh, so you're trying to interact with some other thing that you don't have a good model of. Yeah, so I mean, that might be a truly stochastic control problem, right? That would be not here. Here we're talking about noise in the control policy, right? That would be noise in the environment, like in the dynamics, right? That'd be like process noise, I would call it, maybe. This is like I'm deliberately injecting noise into my control signals. I'm choosing to deliberately add noise to my controller that I'm driving the system with, right?
If you have like a joint space, for example, between me and another thing, like I'm trying to catch something that's running around, and if I cannot really model what the object is doing, then can I say I inject noise to that object?
Yeah, but that's in the dynamics. That's not in my controller, right? So this is a different thing. That would be like, you know, what I'm talking about is like, say I'm, you know, the robot, and that thing's over there maybe wiggling around weirdly, right? That's in like the environment, right? In the dynamics somewhere. I'm saying I'm like adding noise to my joints and like wiggling around like crazy, right? That doesn't really help you catch the ball or whatever. Yeah.
This might be a bit of a previous argument, but I would expect that adding noise to your control policy improves your gradients. Probably makes your programs faster. Obviously, you just made the point that they find local optima, so maybe it's not a great point.
So how would that help? Actually, I'm curious.
Intuitively, if you sample a larger portion of the space, you would have better gradients. If you, with a deterministic policy, you're more likely to fall into.
Maybe. So yeah, there might be some argument for like escaping saddle points and things like this, but generally gradient-based methods are actually pretty good at that on their own, and don't usually get stuck in saddle points and things like this anyway. But yeah, so what it does do for sure is smooth things. So if you have like a non-smooth cost function or some non-smooth weirdness going on in the dynamics, basically what you're doing here is taking a bunch of samples randomly in some neighborhood and then using that to estimate a gradient, right? So like it's going to kind of smear everything out and smooth stuff. So that's potentially one upside, but I would say in general, what you're doing here though is you're computing some like noisy approximation of everything. So in terms of convergence rate, these are strictly worse actually. because you're not getting exact gradients. You're getting
Usually gross
compared to like a non-stochastic actual gradient. This is like some noisy approximation to the gradient, right? So in terms of like convergence behavior, it's not as good as if you had the real gradients. So yeah, I would say like the smoothing thing is real, but really what this is, the reason you do this is it's really a sampling scheme to compute gradients. It's like why you're doing this. It's basically so you can do SGD. And it basically, if you do this, it's yet another way of getting the dynamics to disappear from the problem, essentially. Because if you were to compute the real gradients, you'd need to diff through the dynamics. And here, basically by doing this sampling, you're effectively kind of sort of not really finite diffing. Given a bunch of, you're collecting a bunch of trajectory data, these random samples, and then you're kind of sort of doing like effectively finite diffing on the trajectories to get gradient approximations. Not exactly, right? But something like that. So yeah, I would say the noise is really there as a mechanism to generate samples. To compute gradients. And, there's other ways to do that for sure. But this is, how these things work. Okay, so that's said. I feel like this is super abstract. So to make this a little more concrete, pretty standard assumption in a lot of the robotics applications of this stuff. In terms of what this policy looks like, is deterministic, like U that we talked about having before, plus additive Gaussian noise. So, so what we mean here is that this thing looks like U parameterized by the theta. So we basically have a regular deterministic policy, and we add white noise to it, which we'll call V. And that's drawn from a normal distribution with zero mean and covariance big V. So that's like what is pretty, there's a couple variations on this, but this is like super, super standard. And this is like kind of what people use. So, looking at it this way, it really does feel like basically this is just perturbing around my current policy, right? So I can collect some samples so I can estimate a local gradient approximation, right? Okay, cool. So what are we doing now? Okay, so now we have this noisy control policy that looks like this. Let's write out, we're going to use this a little bit later. So let's write now the distribution over trajectories that you get from this control policy thing, right? And this, we're going to use this later. So here we go. So this gets like super notationally heavy. So I don't know, bear with me. So this is the tau here is trajectories. The theta are the parameters of the controller, right? The weights or whatever. This is a probability distribution. This thing looks like a product. So this is time. So here's the state distribution at time k plus 1, conditioned on state at time k uk. So this is basically the dynamics, right? And then times our policy thing. So these are just fancy stochastic ways of writing dynamics and controller. This is like writing out the distribution, right? Okay, so given this thing, now this is like our distribution over trajectories, right? And this tau is So this trajectory is like, you know, x1, u1, x2, dot, 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 through xn, right? So it's all the states and controls for the trajectory kind of stacked up in one big vector. That's what we mean there. Okay, so now with this thing in mind, I can write out our optimal control problem, which is now a stochastic optimal control problem. So we're going to now be doing min over the thetas, expectation of the cost function, which we evaluate on a trajectory, right? And this is taken with respect to this distribution over trajectories that I just wrote down. Cool. Policy parameters, cost function. Trajectory distribution.
Is that P tau?
Yeah, it's the thing that just above there. P of, that's the probability distribution over the trajectories parameterized by the thetas. This is like the standard notation in the field. I don't love it. I think it's like super notationally heavy and like very abstract, but this is kind of the standard stuff. Okay, so now moving on. We're going to remember the definition of an expectation. Which is, so in this particular case, right, so this guy's tau theta. I'll try to be neat with the handwriting. So this expectation, right, this is the integral over all trajectories of this cost function times the probability density function. E tau, right? So we have this thing over this, this function of trajectories. We have a distribution PDF over the trajectories. We integrate over all possible trajectories, right? That's the definition of expectation. And what we want to do now, this is our cost function, right? That we're trying to minimize with respect to the thetas. So we want to do gradient descent on this thing. So what I want to do now is just take the gradient of that thing with respect to the thetas. So I can do gradient descent, right? So that's the next move. And this is sort of where the classic policy gradient theorem or trick comes up. So what we want is this thing, grad with respect to theta of this expectation of my cost. And if I carry the derivative through, the integrals over the trajectories, right? So theta doesn't show up, so I can bring the derivative inside the integral. And the cost function isn't a function of theta, only that probability distribution is, right? So we're going to diff through the integral and get grad with respect to theta of the PDF. And now we play the famous trick that probably everyone's seen. It's like fun log trick. Okay, so that thing is, so the trick is I'm going to multiply and divide by P, and I'm going to write it like this. So here's what I started with, grad P, and I'm going to divide this by P, I'm going to group these things together inside the bracket, and then I'm going to multiply also by P. So I didn't change anything. And now the thing in the brackets is equal to the gradient of the log of P. So we're going to plug that in. So thing in brackets is the same.
Does it matter if it's the natural log or the log?
It's a natural log.
Okay.
And then now we recognize that this thing that I just wrote down is an expectation, right? It's a thing multiplied by a PDF, integrated over all trajectories. So this thing is, so if I write this all out, this is equal to expectation over this distribution of all the stuff in front of the P. So this times grad log of P. That's the whole thing. Log of, cool. Okay. And there's one last move, which is now what we're going to do is go back to the definition of that distribution over trajectories, which is this product over time steps thing with the dynamics in it. And we're going to diff through that. We're going to like chain or product rule, I guess, into that thing, right? So we're going to take the log of that, which now log of a product is the sum of the logs thing, right? So we're going to get sum over log of P plus log of theta or pi or whatever. So we're going to play that trick, and we're just going to diff through that thing and do the usual stuff. So what's going to happen here, which is kind of important, right, is that the dynamics term doesn't depend on theta. So when I take the grad with respect to theta, that's going to drop out too. So the dynamics go away, right, which is like what we want. And then we're just left with the controller stuff. So that looks like, so this thing is grad of, so here's where I do the, I pull the log inside the product, and I get sum over time steps log of the dynamics distribution thing plus log of the policy distribution apologies for the squishiness. And then this term goes away because it doesn't depend on theta when I take the derivative. So this equals, and I can pull the derivative inside. So we get grad log of the control policy thing distribution. Okay, so if I plug this back in, the final result that we want is grad with respect to theta of our expected cost is expectation of cost function evaluated along the trajectory times this term, which is also evaluated along the trajectory, and it's grad with respect to theta of the log of the control policy distribution thing. Okay, this is the major, put a box around it, result. So that whole mess is called the policy gradient theorem. It basically says like, we can do a bunch of fancy math and end up with this expression that lets us evaluate the gradient of the expectation of the cost function with respect to our policy parameters by evaluating this expectation along trajectories. So the main like important takeaway here is that the dynamics don't show up anywhere in there. And the whole thing is an expectation, which means I can go evaluate it by taking a bunch of sample points from the distribution. So specifically here, what that means is I've got this control policy distribution thing, which we just said is like really in practice, just our actual control policy plus white noise. So I'm going to sample Gaussian white noise basically and add it on to my control policy to get this noisy thing. And I'm just going to do a bunch of rollouts on the system where I just, drive it with that controller, collect a bunch of trajectories. And now this thing is just a sum over those trajectory samples, right, of that thing. And I can evaluate that. The J is just the cost function. And then that log thing over there is just basically derivative stuff from my current control policy, which I can diff through because I know that. So that's the whole thing. So we draw samples from our stochastic control policy. And then we run experiments. Okay, so personally, I find this to be super abstract and it doesn't make a whole lot of sense to me. What you actually do to implement this thing. So what we're going to do next is apply this to the LQR problem that we know and love. We've done lots of stuff with. Yeah.
Can I ask a quick question?
Yeah.
Where the log came from? Maybe I'm just forgetting my log.
Okay, so it comes from up here, this trick. So we have this, we have this grad with respect to this distribution over trajectories in there, right? So what I do is I literally plug in P over P, which equals 1, right? And I just group it. So I have the thing I started with divided by P, and then I grouped it in that bracket, and then I multiply by P on the outside. And what you recognize is that grad of log of P, if I chain rule grad of log of P, I get derivative of the inside thing, which is the thing up top, right? The grad of P. And then the derivative of log is 1 over, right? Stuff. So that's grad of log. That's the trick. Like that one trick is like the whole thing and shows up all over machine learning. I don't know what to call that, like the log trick or something. I think that one trick is basically the policy gradient theorem. And it's very famous. But yeah, it looks kind of cool. It's a fun trick. I don't know. Okay, so far so good. Okay, so the move now is, and let's see, how are we doing on time? Basically, I want to plug in, I want to like do this on the LQR problem now. And the reason is that for LQR, like things are nice and easy, and we actually know the form of the optimal feedback policy, right? It's a linear feedback K matrix. So we don't need to do anything crazy with function approximators. We just plug that in and go to town. So what we're going to do now is min over theta equals K of this expected cost that we've done 1,000,000 times. So So this whole thing, subject to our linear dynamics. Which we assume we don't know anything about. And UK equals minus K X plus this V, where again, VK is drawn from a normal distribution. And we make up this covariance V. It's like a design parameter of the algorithm. So that's what we're going to do. So to do this, I think like this isn't super interesting or fun. Really in practice to do this, you write this down and then call, auto diffing, whatever toolbox, right? But just to like give you a hint, so like we have the cost function, there's J, so we know how to evaluate that on a trajectory. So if I do a rollout, I get a trajectory, I just plug it in and I get the J of tau term. The only missing thing here is this grad with respect to theta of the log of the probability distribution thing. That's super weird. What does that actually look like in this particular case? So I guess I'll start writing it out and maybe we can stop when it gets too ugly. So what the hell is this thing? Okay, so that policy distribution, remember it's just U equals minus KX plus Gaussian, zero mean Gaussian white noise, right? So that means it comes from a Gaussian distribution. So the distribution is a Gaussian, and we all know what that looks like. So here's the distribution. It's got a normalization constant, which I'm not going to bother writing out because it drops out. And then it's exponential of minus 1/2. And here, what we did, right, minus kx, so vk, the noise term, we're saying that's drawn from a zero mean Gaussian distribution, right? So the mean then on that whole thing, the mean of u is minus kx, right? So the distribution here, it's x minus the mean that shows up normally. So that's actually here, uk plus kxk transpose, and then you get v inverse, the covariance inverse, and then same thing over here. So that's the Gaussian distribution. And I want to take the log of this thing, right? So that's easy. It's, sum of the logs. So I get the log C out front plus the log of this exponential thing, which now is just the thing that's inside the exponential. So it's just this nice quadratic function now that gets pulled out here. And now I just want to take the gradient of this thing with respect to the thetas, which in this case is literally just k, right? Which is just a matrix. So I'm just diffing, I'm just chain ruling through that quadratic. It's super easy. You could write this a few different ways. It's sort of like, it's sort of messy, depends how you want to do it. We can use the Cron-Vex stuff that we talked about before. But basically I go through theta, right, equals k. So this is, I'm going to diff this thing with respect to the thing in the parentheses first. And then it's chain rule with partial k, partial theta, whatever, which is the identity. So it turns out it's, use the Cron-Vex stuff. You can write it like this. This isn't super important. Yeah, okay, so that's it. I don't know. Maybe kind of useful, maybe not that interesting, but normally, yeah, like if you use a machine learning toolbox, this is done for you by magical auto diffing. Okay, so this is everything that you need to do this in the LQG case, like written out pretty explicitly. So let's do like pseudocode algorithm for this thing. So the most basic policy gradient method. So first, you're going to initialize with some initial guesses for stuff. We're then going to go sample some trajectories. Sample, we'll call it a batch of trajectories. I guess the term of art is mini batch. That's what people call this. I don't really know why. By just rolling out the dynamics of this, rolling out the system, or like, oops, with UK sample from the distribution. Then you take this batch of trajectories that you just sampled, and you use that batch to you sum over them to evaluate that expectation that gives you the gradient. So literally what you're going to do is the gradient, which we'll call G for now, which is this thing that we just wrote a whole bunch of math to derive. And so this thing, we can approximate this with samples. So if we have S samples, it's going to be sum over these S's. I guess, what did I do here? This is kind of dumb, notation wise. So this thing, I mean, it's the obvious thing. So you get like this sum along the trajectories of this thing that we already know how to evaluate for this particular case. That's the whole thing. So now, and then once we have the gradient, we do a gradient descent step. So we do now theta gets theta minus some step length alpha times G. So step length like we've seen before. Except in machine learning, people call it a learning rate. Let's see, and then you just go to 2 and repeat this. Okay. Questions about that? Yeah.
I assume people are methods for this gradient.
So not so much, it turns out. Like the stated reason is that these problems tend to be very large, and the Newton methods tend to, like, you know, not scale super well to like problems with like millions of variables, especially when there's not nice sparsity structure in the problem. And here, typically things are pretty dense. So you can, like, the weight matrices in the neural networks are typically dense. The networks tend to be pretty big. And if you use the same policy, you know, weights across all the time steps, now those derivatives are all coupled across all of time. So it doesn't decouple nicely in that band structure like you have in a trajot problem. So the matrices tend to be pretty dense, and they tend to be pretty big. So people don't generally use Newton methods. They usually use first order methods, gradient type methods, and tons of flavors of accelerated gradient methods. The closest thing to Newton method that may be in like common practice, practical use, is people do use limited memory BFGS is fairly common, which is an approximate like quasi-Newton methods, but that does get used. But yeah, people generally don't do full up Newton. We have played around with it, and you can make it work. Generally, though, like those second order methods, they have really great convergence when you're close to the optimum, right? When you're far away, So like one option, if you cared to have really accurate answers, would be to like do some first order gradient-y thing for a while, and then when you get close to the answer, you could like polish the solution with like a round of Newton or something. But yeah, generally people don't do this. It's also just generally more expensive to compute like all that Hessian stuff, and a lot of times people don't do it. There are exceptions to this. I think older TRPO algorithms, trust region policy optimization methods, they used Newton CG actually, like in a lot of those methods, which so they were doing approximate Newton stuff to deal with the trust region terms, because those have like second order things going on. But I think in general, people don't do second order stuff. It's very, very uncommon. Yeah.
Is our policy gradient methods only applicable when you have continuous actions? Or-
That's where they get used for sure the most. And I don't really know, like I don't do, discrete state action stuff pretty much at all. So it's really not my thing. I don't think that people use that stuff there. I think those methods you can do like tabular, Q-learning, blah, blah, blah kind of stuff. I think these are pretty much the go-to method for like continuous state action flavored things. Okay, let's do some stuff. Unless anyone has anything else they want to talk about. Here's code. So here's, I don't know, lots to talk about. Let's see. Okay, so here's this on a super benign LQR problem. So 15 time steps, 1D double integrator problem. Wrote down some cost matrices, stuff we've done before, cost function. Here's a ground truth solution. So this is the true optimal policy, right? The LQR solution. Here's closed loop sim of this for fun. Cool, drives it to the origin super fast. Here's policy gradient. So we're gonna run it for 1,000 iterations. This batch size is how many trajectory samples we do, right? These are a bunch of algorithm parameters. This is basically your step length. This we'll talk about in a sec. This is my noise covariance. This was, I played around with process noise, but I set it to 0, so it's deterministic. Initialize the K matrix with zeros. Talk about this in a sec. And then, yeah, the rest of this is just storing stuff. Okay, so first thing I want to do is super vanilla stochastic gradient descent, which is exactly like the thing we just wrote down. It turns out this doesn't work. Like it totally fails, and you need a hack to make this work. It's called a baseline. Who's seen this before? Like everyone's seen this before. So it turns out there's various things you can do here, but the like cool thing to do there is actually to plug in a value function here. And so this is where like actor critic stuff comes in. Basically, you estimate the value function and stick it in here. We're not going to do that. We're going to do the dumb version, which is to just plug in the average cost over the trajectory samples here. It turns out I tried a bunch of things that this straight up does not work without a baseline thing in there. So the stock vanilla versions don't work without some hacks. But otherwise, this is exactly what we did. So this is just subtracting a constant off, which seems like it shouldn't really affect the answer, but it apparently makes a big difference, which I feel vaguely uncomfortable about. Okay, so yeah, this is like we sum over the batch, the thing we wrote down. This is that baseline thing, which is the average cost. I'm just subtracting off the average. I take the gradient step, and then I roll it out to get the cost. So we'll run this for 1,000 iterations of 50 samples. So this is 50,000 individual rollouts, right, that I'm doing. Let's go plot some stuff. Oops. So this is cost versus, oh, that didn't go well. What happened? It definitely worked before class. So unless I super screwed something up somehow, that looks better. I don't know what just happened. Okay, that looks pretty. Here's the like ground truth cost from the real LQR policy. This is what we just got, so it's pretty close. Let's look at the K matrices. So this is the ground truth LQR one. This is the one we just got. So it's actually, the K matrix is not very close. The costs are pretty close though, and that's what we're optimizing for. Let's look at the rollout. So this looks a little bit different, right? Than like, so it's not super close, but it's getting there. Okay, so that's like as vanilla as I could make work. Modular that little baseline hack. The other thing that might be kind of fun is, okay, so turns out this atom, probably a lot of you heard of this. This is an accelerated gradient descent method. So it uses some tricks. Basically, what it really is kind of a bad approximation of LBFGS. It uses momentum, like, so it uses past gradient evaluations to try to speed up progress. Otherwise, it's the same. That's what's going on here. Everything else is the same. Turns out this works a lot better than the vanilla stuff. And actually, on this problem, we can basically get the optimal thing with this. Okay, so there it looks, the curve looks the same, but turns out this gets a lot closer, and really the K matrix looks a lot better, right? It's basically there to a couple decimal places, and this looks like dead on. Cool. Okay, so this is as easy an LQR problem I can write down. It's 2D, double integrator dynamics. It's open loop stable, right? Let's do a slightly harder still LQR problem. This is the 2D quad rotor linearized that we did with LQR like a long time ago. The same stuff from like those earlier notebooks. And we're going to linearize about hover, and I'm only going to run it on the linear dynamics, just the LQR stuff, right? But the main, okay, let's just do it. So this is a 6-dimensional state, 2 inputs, blah, blah, blah. Otherwise pretty similar. I'm giving an initial offset, like a meter over a meter, half a meter off in the Z, cost function, blah, blah, blah. Ground truth, LQR gains, blah, blah, blah. This all works, cool. So here's, we're gonna do the same exact thing. I played with the parameters a little bit to try to get this to work. So batch size is bigger. I don't know, most of the stuff's the same though. Just gonna, and here we're only gonna do atom because the other stuff just doesn't work. And this is gonna take a while, but the punchline is this sort of works. Oh, this doesn't work. Well, so, okay, this is actually worth looking at. This is gonna take a while, so we'll use the stale numbers. This is kind of what comes out of this thing. And these are fairly representative. So this really doesn't converge. And it turns out if you like try harder and give it more play around, it kind of never does. And one interesting thing that like comes out of this, let's see if this finished. Nope. Okay, so like, why doesn't this work? So it's remember, it's driving this thing with random actions pretty much at first. A big difference between this and the last system is that this system's open loop unstable. So if I start it out like in this hover and I give it random noise, it's going to just flop over and like kind of blow up on you, right? Which is not great. And it turns out like if you check the closed loop eigenvalues of the system with the K matrix that this thing optimized after 1,000 iterations, it's still unstable. The closed loop system's unstable, right? So this thing basically like, it's just flailing around with random noise and like it never finds a stabilizing controller. So I think there's some deeper things to say about this. Basically like this sort of random input sort of vibe probably doesn't work great. Okay, now we can actually look at this stuff. If you have an open loop unstable system, this might have worked a little better. Now it looks kind of still like garbage. But yeah, look, the costs are kind of terrible. The true K and the thing that this fit don't look anything like each other. Closed loop, yeah, super unstable still, right? Eigenvalues greater than 1. I think that's about all there is to say about that. So here's the final thing I want to leave you with. What I'm going to do now, so this is all like model free, blah, blah, blah. What I'm going to do now is like the dumbest thing I can possibly write down to optimize this given some model information. So I'm going to solve the same problem. Everything else is the same. Blah, blah, blah. Here's where it gets different. This is all the same. Instead of this SGD policy gradient thing, I'm actually going to just take the gradient with respect to the policy of the cost function, like through the dynamics model. And I'm going to do everything else the same. But yeah, you can see what this looks like. I'm literally doing forward diff through the cost function with respect to the Ks. And then I'm going to do like a similar gradient momentum-y thing. And I'm going to do a line search. That's the other big thing. The other stuff, we didn't have a line search, right? So if I run this, 300 iterations, it like totally nails it. And it gets basically the, more or less the exact same K matrix. The costs are almost the same. And like, it's stable, closed loop stable, and the rollouts look pretty much identical to the stuff that we got from like the optimal thing. So let's see, a couple minutes left. That's like, I think that's all I wanted to show you. Let's see. Okay, so concluding remarks. Basically, I would argue that these policy gradient things, they're probably assuming too little knowledge of what's going on. And in particular, like, okay, so let's write some stuff. So I should say, like my implementations, these are super naive, right? You can obviously do better things, but I think the general trend, I was also running them on the easiest possible problems you could invent, basically, right? So I mean, that's sort of fair. So I don't know. A few more tricks are needed to make this stuff work in practice. I'll post the code too if you guys want to play with it. If anyone wants to implement like, state-of-the-art RL algorithms on top of this, that'd be cool too. And then, yeah, the other thing is like we were doing 1,000 things with like 100 or 1,000 batch size, so like order 100,000 individual rollouts, right? Whereas when I did it with the real gradients, I did like, and I was still getting crap results basically, right? Whereas I did like a couple hundred rollouts with real gradients and got like just nailed it, right? So I would say these things are pretty sample inefficient, which is like a known issue. Compared to real gradients. Okay, so yeah.
Does anybody like to just like deterministically sampling?
Seems like a good idea, right?
Yeah.
Yeah. So a few people have, but it's surprisingly unpopular. Emo Todorov did a bunch of this stuff like 10 years ago. The Mujoko guy did things like this, where you just actually diff through the simulator and get the real gradients. But here's some like, I don't know, parting thoughts for the day from me. So first of all, I will say controversial things now. So I would argue that RL trained in simulation, which is what everyone does because they're not sample efficient enough to get enough data on hardware. RL trained in simulation is model-based control. Like you're just pretending it's not. That's what I would argue. Like literally, if you are doing this in a simulator, there are equations inside the simulator for everything that's going on that someone coded up, right? And you're just ignoring them. You're doing model-based control. You have a model inside your simulator. You're just ignoring it and doing black box sampling, which is not maybe the best thing to do, number one. And then also like, you can dramatically improve sample efficiency and convergence behavior by like leveraging a little bit more model information, right? Namely gradients of the model, right? So the stuff we did there, by the way, even if we have a bad model, I can still get gradients through the bad model. And those gradients will still probably be better and way more efficient than the stochastic sample, approximate gradients I get with this policy gradient stuff. So like, that's a whole thing. That's basically what ILC is.